Welcome to G Fun Facts Online. Today we are going to change the way you perceive the empty space above your head. For the entirety of human civilization, astronomy has been a silent science. Think about it. When we looked up, we traced the arcs of planets. We mapped constellations. We eventually built glass lenses and polished mirrors to peer into the deep past. We learned to see the universe in visible light, then in radio waves, then X-rays, and infrared. But throughout all of that history, the cosmos was effectively a pantomime. It was a silent movie of violent explosions and serene orbits, played out on the velvet screen of night. We could see the flash of a supernova, but we could not hear the crash. That changed fundamentally in 2015. That was the year the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first gravitational waves. It was a chirp, a fleeting, high-frequency signal that lasted less than a second. It was created by the collision of two stellar-mass black holes. That event was a violent shout in the dark, a singular event that proved space-time itself could vibrate. But here is the thing about that discovery. It was just a transient crash. Beneath those sharp, short chirps lies something far more profound. Something that has been washing over the Earth for its entire existence, unnoticed, until now. It is not a shout, but a murmur. It is not a single note, but a chord played by billions of instruments simultaneously. It is the cosmic hum, a low-frequency, stochastic background of gravitational waves that permeates every cubic centimeter of the universe. In June 2023, a global coalition of astronomers announced that after 15 years of staring at the ticking clocks of the galaxy, they had finally heard it. This is the story of that hum, the supermassive monsters that create it, and the decades-long vigil required to catch the heartbeat of the cosmos. To understand this hum, we have to start with the medium through which it travels. We have to go back to 1915 and Albert Einstein. His general theory of relativity upended the Newtonian view of gravity as a force. Einstein proposed that gravity is actually the curvature of spacetime itself. The famous maxim is that mass tells spacetime how to curve, and spacetime tells mass how to move. The classic analogy is a bowling ball placed on a trampoline. It stretches the fabric, creating a dip. If you roll a marble nearby, it orbits the bowling ball, not because of an invisible tether, but because it is following the curve of the fabric. Now, imagine that bowling ball is not stationary. Imagine two bowling balls spinning around each other furiously. The fabric of the trampoline wouldn't just curve, it would ripple. Waves would spiral outward from the center, carrying energy away. In our universe, these ripples are gravitational waves. It is crucial to understand that these are not waves in space. They are waves of space. As a gravitational wave passes through you, it doesn't just push you. It stretches you in one direction and squeezes you in the other, changing your very physical dimensions before returning you to normal. The stiffness of spacetime is unimaginable. To create a ripple significant enough to be detected by human instruments requires violence on a cosmic scale. The chirps detected by LIGO come from black holes about 30 times the mass of our Sun, whirling around each other hundreds of times per second. These produce high-frequency waves, like a soprano's voice. But the universe is home to things far larger than stellar black holes. In the hearts of most galaxies lie supermassive black holes. These are giants with masses millions or even billions of times that of the Sun. When galaxies merge, these titans sink to the center and eventually find each other. They begin a slow, doom-laden waltz that can last for millions of years. They orbit not hundreds of times a second, but perhaps once every few years or decades. The waves they produce are not short chirps. They are long, rolling undulations, with wavelengths measured in light years. A single wave crest might take a decade to pass the Earth. These are the bass notes of the cosmic symphony. And because there are merging galaxies scattered throughout the depth of the universe, these waves overlap. They create a confused, chaotic background noise. This is what we call the stochastic gravitational wave background. It is this background hum that astronomers have been chasing. But here lies the engineering challenge. To hear a sound so deep and so slow, a detector on Earth is useless. You cannot build a ruler long enough to measure a wave that is light years long. To catch these waves, you need a detector the size of a galaxy. Nature, fortunately, has provided us with the perfect instrument, the pulsar. Pulsars are the rapidly spinning corpses of massive stars. When a giant star dies in a supernova, its core collapses into a neutron star. This is a sphere only about 20 kilometers across, but packing more mass than the Sun. These objects are incredibly dense. A single teaspoon of neutron star material would weigh 1 billion tons. They are also highly magnetized and spin at dizzying speeds. Beams of radio waves blast from their magnetic poles. As the star spins, these beams sweep across the sky like the light from a lighthouse. If the Earth happens to lie in the path of the beam, we see a regular pulse of radio waves. Blip, blip, blip. Some of these objects, known as millisecond pulsars, spin hundreds of times per second. They are the most accurate clocks in the universe. Their rotation is so stable that they rival the precision of our best atomic clocks. If a millisecond pulsar is timed to arrive at a specific nanosecond, it will arrive at that nanosecond, reliable for millions of years. This stability is the key. If space were perfectly still, the pulses from these cosmic clocks would arrive on Earth with absolute regularity. But if a gravitational wave is passing through the galaxy, it stretches and squeezes the space between Earth and the pulsar. When space is stretched, the radio pulse has to travel a slightly longer distance, so it arrives a tiny fraction of a second late. When space is squeezed, it arrives a tiny fraction of a second early. By monitoring a network of these pulsars, what we call a pulsar timing array, astronomers can look for these telltale deviations. However, the effect is vanishingly small. We are talking about changes in arrival time on the order of tens of nanoseconds. That is billionths of a second, spread out over years of observation. Detecting this requires not just precision, but patience. It requires timing the arrival of pulses to within the width of a hairpin from stars thousands of light years away, while the Earth spins, orbits the Sun, and wobbles on its axis. The search for this background hum has been a marathon, not a sprint. It is an effort that has spanned continents and generations of careers. The primary players in this global hunt are three collaborations: the North American Nanohertz Observatory for Gravitational Waves, or NANOGrav, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia. Together with the Indian Pulsar Timing Array, they form a global consortium. The methodology is grueling. Astronomers must visit radio telescopes, giant dishes like the Green Bank Telescope in West Virginia, the Lovell Telescope in the UK, and formerly, the legendary Arecibo Observatory in Puerto Rico. They go week after week, month after month, year after year. They point these dishes at dozens of chosen pulsars, recording the arrival times of the pulses. The data accumulates slowly. A single year of data is useless. It is just noise. 5 years is barely a start. 10 years, and you might see a hint. It takes 15 years or more for the signal to rise out of the static. This long watch has not been without tragedy. The Arecibo Observatory, a titan of radio astronomy nestled in the jungle of Puerto Rico, was the workhorse of NANOGrav. Its massive 305-meter dish provided about 50% of the sensitivity for the NANOGrav data. In 2020, after a series of cable failures, the instrument platform suspended above the dish collapsed, destroying the telescope. The loss was devastating to the scientific community and to the people of Puerto Rico, for whom Arecibo was a cultural icon. But Arecibo's ghost lives on in the data. The 15-year dataset, released by NANOGrav in 2023, contains years of exquisite observations from Arecibo, a final posthumous gift that was instrumental in the discovery of the hum. The discovery itself was not a single moment of eureka, but a slow dawn. In 2020, NANOGrav released their 12.5-year dataset. They saw a common red noise process. It was a signal that looked like the hum, but they couldn't be sure. It could have been a quirk of the clocks, or an error in the model of the solar system's center of mass. They needed more time. 3 years later, with the 15-year dataset, the picture sharpened. The signal was there, and it was stronger. But more importantly, it had the right shape. This leads us to the crucial question. How do you know that a variation in pulse timing is a gravitational wave, and not just something wrong with the pulsars themselves? If all the pulsars were just glitching randomly, there would be no pattern between them. If the atomic clocks on Earth were wrong, all pulsars would show the exact same error simultaneously. If the solar system ephemeris, our map of where Earth is, was wrong, the error would look like a dipole, a specific sway caused by our incorrect position. Gravitational waves leave a unique fingerprint known as the Hellings-Downs correlation. Because gravitational waves are quadrupolar, meaning they stretch and squeeze, they affect pulsars in different parts of the sky in a very specific, mathematically predictable way. If two pulsars are close together in the sky, their timing delays should be correlated. They are both stretched or squeezed similarly. If they're separated by 90 degrees, they should be anti-correlated. One is squeezed while the other is stretched. If they are 180 degrees apart, they are correlated again. When you plot the correlation between pulsar pairs against the angle separating them in the sky, the points should fall along a specific curve, the Hellings-Downs curve. This curve is the smoking gun. There is no known astrophysical noise source that mimics this pattern. It is the signature of general relativity itself. In the 15-year data release, for the first time, the data points from NANOGrav and its partners didn't just scatter randomly. They hugged the Hellings-Downs curve. The statistical significance was between 3 and 4 sigma. In scientific terms, this is compelling evidence. It effectively means there is less than a 1 in 1,000 chance that this pattern is a fluke. While particle physicists often demand 5 sigma to use the word discovery, the astrophysical community widely recognizes this as the detection of the background. The hum is real. So what is making this noise? The leading theory is as majestic as it is terrifying: the slow-motion collision of the largest objects in the universe. We know that galaxies merge. The Hubble Space Telescope has shown us beautiful, chaotic images of galaxies colliding, their stars thrown into wild streamers. We also know that every massive galaxy has a supermassive black hole at its center. The Milky Way has Sagittarius A, a black hole 4 million times the mass of the Sun. The galaxy M87 has 6.5 billion times the mass of the Sun. When two galaxies merge, their black holes don't hit each other immediately. They sink to the center of the newly forming galaxy, drawn by gravity. They form a binary pair, orbiting each other. As they orbit, they interact with the surrounding gas and stars, kicking them away and losing energy, which causes them to spiral closer. However, theory predicts a bottleneck. When the black holes get to within about 1 parsec, or 3.26 light-years, of each other, they run out of stars to kick out. They are too close to interact with the galaxy at large, but too far apart to emit strong gravitational waves that would drive them to merge quickly. They should stall. This is known as the last parsec problem. If they stalled there forever, they would never merge, and there would be no gravitational wave background. The detection of the cosmic hum solves the last parsec problem observationally. The fact that the background is this loud means these binaries are overcoming the stall. They are spiraling in. The hum is the collective groan of millions of these binaries, slowly grinding toward merger across cosmic time. The loudness of the signal was actually slightly higher than many theoretical models predicted. This implies that either supermassive black holes are more massive than we thought, or they merge more efficiently than our simulations suggested. It suggests the universe is a rougher, more dynamic place than we assumed. While supermassive black holes are the standard explanation, they are not the only possibility. The hum could be a message from the very beginning of time. Cosmologists have long speculated about exotic sources of gravitational waves that could have been created in the fraction of a second after the Big Bang. One possibility is cosmic strings. These are hypothetical one-dimensional topological defects, essentially cracks in the universe, formed during phase transitions in the early cosmos. Imagine ice freezing. Sometimes cracks form where the crystals don't align perfectly. Cosmic strings would be effectively infinitely thin tubes of energy stretching across the universe, possessing immense mass. If they exist, they would vibrate and snap, creating gravitational waves. The NANOGrav data places tight limits on these. If they exist, their tension must be very low, or we would have heard a louder hum. The current data disfavors stable cosmic strings as the sole source, but they cannot be fully ruled out as a contributor. Another possibility is primordial inflation, the theory that the universe underwent a rapid exponential expansion in its first moments. This violent expansion would have generated gravitational waves. However, the standard inflation models predict a background far too faint to be the signal NANOGrav detected. If the hum is from inflation, it requires blue-tilted models, non-standard theories, where the energy spectrum rises at higher frequencies. Then there are phase transitions. Just as water turns to steam, the early universe went through phase transitions as it cooled. If these transitions were violent first-order transitions, involving bubbling pockets of the new vacuum state colliding, they would generate gravitational waves. Currently, the data fits the supermassive black hole hypothesis best. It has a spectral index of -2/3, which matches the prediction for binaries. However, as the data improves, astronomers will look for deviations from this smooth spectrum. A bump or a dip in the hum could reveal one of these exotic cosmological sources hiding underneath the black hole signal. We are effectively doing archaeology of the Big Bang, using gravity. The detection of this background is a triumph of signal processing, as much as astrophysics. The signal is incredibly faint, buried under mountains of noise. The primary enemy of the pulsar astronomer is red noise. White noise is random static, which is easy to average out. Red noise is correlated noise. It wanders. It's like a drunkard's walk. Pulsars themselves have intrinsic red noise. Their interiors are superfluids of neutrons, and sometimes they spin up slightly or wander in their rotation due to internal turbulence. This spin noise looks suspiciously like the slow roll of a gravitational wave background. Then there is the interstellar medium. The space between stars is not empty. It is filled with tenuous plasma and free electrons. As radio waves travel through this plasma, they are slowed down. Lower frequency radio waves are slowed more than higher frequencies. This is called dispersion. The problem is that the interstellar medium is turbulent. It changes. A cloud of gas might drift across the line of sight, changing the dispersion measure and delaying the pulse. This space weather can mimic a gravitational wave. To fight this, astronomers observe pulsars at multiple radio frequencies. ISM effects depend on frequency, while gravitational waves affect all frequencies equally. By comparing the arrival times of high-frequency and low-frequency radio waves, they can subtract the ISM noise. This is why the loss of Arecibo was so painful. It was capable of observing continuously across wide frequency bands, making it excellent at cleaning up this space weather. The detection of the Hellings-Downs correlation is the mathematical proof that they have successfully filtered out the pulsar red noise and the ISM weather. Intrinsic noise affects only one pulsar. ISM noise affects one line of sight. But the background hum affects them all, in a correlated pattern. The detection of the cosmic hum is just the opening movement. We have entered the era of multi-messenger gravitational wave astronomy. We are building an orchestra of detectors that span the entire frequency spectrum. At the high-frequency audio band, we have LIGO, Virgo, and KAGRA, continuing to listen for the chirps of stellar black holes and neutron stars. They tell us about the death of stars. In the mid-frequency range, the gap, we look to the future. In the 2030s, the European Space Agency will launch LISA, the Laser Interferometer Space Antenna. It will consist of 3 spacecraft flying in a triangle millions of kilometers apart, firing lasers at each other. LISA will be sensitive to millihertz frequencies. It will hear the mergers of massive black holes and the inspirals of white dwarfs. It will be able to verify the populations of black holes that eventually grow into the monsters PTAs detect. And for the low frequency, the deep base, pulsar timing arrays will continue to grow. The next game changer is the Square Kilometre Array, currently under construction in Australia and South Africa. The SKA will be the largest radio telescope ever built. It will not just time dozens of pulsars, it will time thousands. With the SKA, the resolution of our gravitational wave picture will increase dramatically. We will move from simply detecting the background hum to resolving individual sources. We will likely be able to point to a specific galaxy and say, there. 2 supermassive black holes are merging right now. This will allow for multi-messenger astronomy on a galactic scale. We could detect a continuous gravitational wave from a binary in a distant galaxy, and then point our electromagnetic telescopes at that galaxy to see if the accretion disk is flaring or behaving strangely. We will be able to watch the dynamics of a merger in real time, seeing the gas swirl as the spacetime ripples. For the entirety of human existence, we have been deaf to the universe. We have watched the lightning, but never heard the thunder. Now, we can hear the rain. The detection of the gravitational wave background is more than just a data point. It is a fundamental shift in our relationship with the cosmos. We are now measuring the breadth of the universe, the slow, rhythmic expansion and contraction of space caused by the most massive objects in existence. It tells us that the universe is dynamic and noisy. It tells us that galaxies don't just sit there, they dance, they merge, and they grow. It validates Einstein's vision of a flexible, responsive spacetime. As the years go on, the hum will resolve into a song. We will pick out individual notes, the specific binaries, the exotic echoes of the Big Bang. We have built an ear the size of the galaxy, and for the first time, we are truly listening.